Hi, I'm Ray Myers. Welcome to No Pilot, where we discuss the state of AI coding agents. And particularly today, we're going to talk about SWE-bench and how to interpret the scores, which is a topic that's become intertwined completely with this space. So, as you probably know, SWE-bench is a benchmark that measures the performance of AI coding agents on realistic tasks that are actually taken from issues that needed to be solved on open source repos on GitHub. It provides an incomplete yet very useful view in what the usefulness of these agents is going to be in a practical context, which definitely separates it from earlier benchmarks. For example, Human Eval, which was doing kind of isolated tasks. The tasks in SWE-bench operate on the context of an entire code repository, and that makes them a very strong indicator of ultimate practical usefulness. Like we generally agree this score represents some sort of proxy for how useful this is going to be. Take or leave whatever confounding factors there are that we're going to discuss. So first, let's talk about the state of the art, or you're going to see this abbreviation a lot around, SOTA. That means state of the art at any given moment. Was the highest performance that has been achieved. That is generally thought to be about 50 to 55% on the verified subset of SWE-bench. There are different subsets of the benchmark. We're going to get to that as well. So the current leaders, and this is the scores that have been confirmed on SWEbench.com, which Princeton operates, who made the benchmark. It's changing all the time, but currently the overall lead is a proprietary tool, Amazon Q developer, and the open source lead is Open Hands Codact. Full disclosure, I do work for All Hands now. That's new. Anyways, there are a number of other open source agents that are performing in that sort of range. Codact is leading right now. You could also say there's kind of a state-of-the-art model right now, even though this is an agent test, because of the agents we know the architecture of. The ones that are performing the best are all right now using Claude 3.5 Sonnet. O1, we believe, also is very strong on this kind of test, but it is very slow. It's kind of impractical to point your agent at it. You could see maybe doing a hybrid approach where O1 was involved in some of the more difficult decision making, and you were using smaller models for more of the heavy lifting. But generally, O1's strong, O1's very difficult to actually run. And magnify that a bunch of times for the new O3 model, which OpenAI has just announced, but is slated to come out around March. As far as we know, it will be insanely slow, insanely expensive, at least based on their early tests. What they were reporting is some of the other tasks. I don't know that they reported the cost of the SWE-bench tasks, but others were taking sometimes thousands of dollars for an individual task. So they did report a staggering on the verified subset of SWE-bench, a staggering 71.7%, which would be, almost 20 points above the state of the art. But with that, with it being such a more computationally expensive thing to run, it's not even clear if this is a fair apples to apples comparison. What are some other misconceptions that people have when they interpret SWE-bench scores? It's great to see the increased relevance of this benchmark. A lot of us, when we first saw it, knew like this is kind of where things need to go. But with that increased relevance comes a lot of confusion. So the first thing to understand is things that are just common to any benchmark that gauges the performance of an AI system, like a large language model or an agent. And the first thing there is don't compare human performance to the performance of machines on a benchmark. When we evaluate humans through standardized tests and many other ways, we are calibrating an evaluation based on the known strengths and weaknesses of humans. And so, for example, it is meaningless to take something like a bar exam and then give it to an LLM and then compare the scores A to B. We've had LLMs that could do well in a bar exam for almost 2 years now, let's say, and we understand perfectly well they can still not practice law because you cannot compare scores human to machine on a benchmark. It's an interesting data point, but even on something that's more practical, like a SWE-bench, I urge extreme caution comparing A to B. Human exams are not calibrated for machines, vice versa. The second major point about benchmarks going to benchmark is that one benchmark is never the end of the line. There are people that sometimes speak as though when we get towards saturating a benchmark, which means achieving such high performance on it that the scores are kind of no longer meaningful, that's what saturation means, then we should just all admit that AI has been finally achieved for some definition. Like, that's not really how this works. It's a cycle. It's an ongoing improvement cycle where we identify one weakness we seem to have and how to measure it. We work towards saturating that particular benchmark, and then we identify the next weakness. It's not really like something as definitive as, say, if you're benchmarking the performance of a JSON serializer or something, where it's like definitely taking the number of seconds that you think it is. We're dealing with proxy metrics. We're dealing with very multifaceted areas of performance. We're just our understanding of how to think about and even measure this concept, co-evolves with the benchmarks, and that's just fine. After we saturate SWE-bench, we'll have something else. Benchmarks become saturated and we find new ones. That's all there. So, second misconception is the sampling. I'm seeing a lot of confusion on what exactly the significance of these percentages is. So, for example, if you score 50% on SWE-bench verified subset, and what those examples are is they are taken from GitHub tasks that needed to be done in Python repositories, which is true. Does that mean that you can do 50% of the tasks in those Python repositories? No. Actually, surprisingly, no, it doesn't mean anything of the kind, right? The score in SWE-bench does not mean the percentage of all pull requests on GitHub that you would want to point one of these tools at, because there is sampling bias. Specific examples were chosen for their suitability in this benchmark, and that's non-trivial. That makes a huge impact. The general consensus is these percentages represent what it could do on some useful subset of the work we've got, and that's the best we're going to have for now. We don't fully understand exactly what that subset is, what the impact of that will be, but we know that it is pretty useful and significant. But we definitely should not conflate it with being able to solve that same percentage of all the pull requests on GitHub, as I've seen many media outlets do. That's not at all what's happening. So another thing is where these examples are from. That's another reason they are not all the pull requests on GitHub, is they are specifically from some a handful of open source Python libraries. And that was a perfectly reasonable place to focus, but understand that you cannot then even go so far as to point one of these agents at like an open source Java library or an open source OCaml library and expect remotely comparable performance. We generally believe that with enough time and training, we could achieve that through similar techniques, but that's not what these things are going to do. They are tuned for this particular context, let alone if you do what we really need to do and take them inside corporate walls and expose them to a bunch of stuff that is kind of bespoke for local context and is not in the training set. Now, another way that this is kind of confounded in the way that it's sampled is these tasks have to fit well into a benchmark. So this is going to select for simple and well-defined tasks. That's again, non-trivial, right? Oftentimes the things that are the simplest, well-defined things that you would be able to put in benchmark are not really the things that are the most difficult, right, in our profession. So we don't know exactly how that shakes out. Again, we think that these are useful tasks. We do want agents that can do these things, but just the selection of assembling the benchmark across several dimensions has limited the generality of what we're really talking about. We have to be clear on that. So 3 is understanding the subsets of SWE-bench. The initial SWE-bench set, which we now might call SWE-bench full, was about 2,000 examples. And some people do still run on it, but it's not always practical to do that. If you imagine, some of these agents will take several dollars per task, though it's great if they cost less, right? And just to produce a score, you're spending several $1,000s. Now imagine like iterating your agent. So because this was impractical, and also because we were unclear of how many of them were even possible, a couple subsets called SWE-bench Lite and then SWE-bench Verified were produced. So Lite was the first official subset, and then Princeton, in collaboration with OpenAI, released the SWE-bench Verified subset. And so Lite is smaller, and Verified is like Lite, except we have made sure they're all possible to solve. So that is seen as our clearest signal right now. As I say, usually when we're talking about scores, we mean SWE-bench Verified now. But last April, when we were talking about the first reputable scores, that was usually in the realm of 15% on a sampling of SWE-bench full. That's not apples to apples with SWE-bench Verified, actually. It might be 25, it might be 30% would be my guess, is what we were actually dealing with in April, but we've changed the subset that we look at. So really between April and now, the numbers we were talking about, I'm going to try to just make this clear. The numbers we were talking about from April to now were 15% and then now 50%. But in my opinion, if you were talking about apples to apples performance, it would be more like 30% up to 50. Hope that makes some sense. Anyway, so agents versus models. We talk about O3 is coming out. It can do this on SWE-bench. Well, is O3 even a model, or is it an agent? Did they mean O3 wrapped in an agent? This is not really clear. They haven't explained what exactly they did to produce that. But I want to be clear that if you were talking about a raw model, it's not actually able to address SWE-bench on its own. The scope of a SWE-bench task is an entire code repo. You can't put that in a single prompt. So it would always be the combination of an agent and a model. And it has generally been the case that the biggest gains have been coming from new agents, better agents. The coding agents that the coding models, that is to say, that we've had a chance to work with have all been about the same strength since SWE-bench was initially released. We'll come back to that. So this is why we think of SWE-bench mostly as an agent benchmark, although there have been some amounts of improvements that came from better models. Most of them came from better agents. We still have a lot to learn about how we can use LLMs as a component to the fullest by surrounding them with more effective tools, right? And I mentioned earlier, right now Claude Sonnet 3.5 is the best that it is practical to use. These are all basically GPT-4 level, though. So because GPT-4 had already been released when SWE-bench was released, and we're learning how to use it, we've basically had the same amount of horsepower available for these agents for the entire time that SWE-bench has been around, right? So that's why it's been mostly agent improvements that have made the difference, though. Again, models have made some. This may change, right? With O1, with O3, that trend may change a lot. Next factor we should talk about is contamination. So because these examples in SWE-bench are in open source repositories, they and indeed are now in a highly publicized benchmark, they're subject to not only deliberate but even accidental contamination. Contamination is when the thing that you're trying to measure against makes it into the training set of a large language model, for instance. So that would mean that we wanted to gauge its performance kind of organically at this kind of task, but what's actually happened is it has just memorized the exam. That's not good. And so that has started to become, an increasing concern. This is one of the big goals of the Konwinski Prize, actually, that I talk about in my last video, is they're going to gauge SWE-bench-like scores to determine the winner, which probably won't be the full $1 million. That threshold will probably not, but it'll probably be tens of thousands of dollars, at least pretty respectable. That is to not get the current SWE-bench examples a score on them, but it is on an undisclosed new example set that is going to be revealed after the contest. So this is kind of resetting the clock and making sure, do we really have a clear signal on what's achievable with the current state. And the other thing that makes Konwinski Prize really unique, I think, is that it's a focus on open weight models. And although I've mentioned many open source agents over the course of this, I did not, in this video so far, mention any open weight models because they are not considered competitive with, for this kind of use, even though there are some pretty good coding models. So we're going to have to figure out how to make that work, right? If we want to win that money. Anyway, hope this was helpful. This is a very subtle topic. If you feel like there's anything you'd like to add, comment sections are right there. And best of luck if you're competing in the Konwinski Prize. I'll also share a place where I'm gathering some tips, but I will not be playing to win personally. So have a good one. And as Lao Tzu said in the Tao Te Ching, with patience, the most tangled cord may be one. This was one take. This was all one take. The most tangled cord may be undone.